All right. Hello, everyone. My name's Kelly Olson. I work for a company called Supranational. And just as a brief bit of background, at Supranational, we focus on hardware acceleration of cryptography. And so in this talk today, I'm just going to sort of expand on some of the themes that Justin had talked about and sort of give a little bit more detail on the hardware performance, both on latency and throughput of various architectures. And there will be a talk on this at SBC with even more details, so please go watch that. I'll put a plug in at the end of this for that. So just to talk briefly about our involvement in the VDF Alliance, our goal is really to move these constructions from idea to implementation. And so what we'll talk about today is sort of how we've used different hardware platforms, different cloud services to really create a complete functioning VDF solution today. And then we'll also give a little bit of insight about how the performance of that will improve as you move to custom hardware. And really our goal as a company is to unlock the compute capacity of hardware present in the ecosystem. So you have 10,000 nodes on Ethereum with CPU capacity. There's maybe something like 3 million GPUs that are currently mining on the network. And there's a lot of opportunity as we look at FPGAs and ASICs to really add these sort of extra protocol accelerators that can really just improve the capacity of blockchain networks. And as always, open source and collaboratively built is the name of the game with the VDF Alliance, and that's what we do. So just to talk very briefly, this is a bit of a landscape of everything that's going on that Justin alluded to in terms of groups of unknown order. And you'll get to hear from a number of speakers today about these various topics. And you can also go back. All of these talks are online on vdfresearch.org if you want to learn about any more of these. But from our perspective as a hardware company, really what we're going to be focusing on is various hardware platforms and then various arithmetic operations. And the really neat thing about these problems and these use cases and constructions is that at the end of the day, they basically boil down to two operations: modular multiplication and modular squaring. In some cases, maybe things like scalar multiplication or exponentiation. So today I'm going to talk in particular about the VDF use case in general across these different platforms. So to talk about the evaluation part of the VDF, this is really the same thing as a time lock, and this is ultimately a latency-focused hardware operation. So what you want to do, the basic concept, is to square a number as quickly as possible. And in the case of the RSA VDFs, which is what we'll be talking about today, this is 1,000 to 3,000 bit modular squaring. So last year, Erdinch, who's here, presented a low latency algorithm for fast squaring on an FPGA. And shortly thereafter, we went and we implemented this algorithm on an FPGA. And what we were able to do is move from about 700 nanoseconds per squaring operation down to 70 nanoseconds on the FPGA. So we're able to get about a 10x improvement here versus what was possible on the CPU. So what did we do with that? We went and cracked a 20-year-old puzzle at MIT. So here's a picture of a number of the VDF Alliance folks with Ron Rivest. This is a puzzle called LCS 35. It had been outstanding for about 20 years. It basically required you to square a number, I think, 70 billion times? 70 trillion times. And we were able to do this in about 2 months. Unfortunately, about a week before we finished, one of the gentlemen in here had actually been running that same operation on a CPU for about 10 times longer. And so just by chance, he ended up beating us just by a couple weeks. But it's an amazing story. He had moved multiple times. He had been running this on his dev machine, so he was browsing the internet and for the past 3 years while this was running on one of his cores. So it was a well-deserved win on his part. So while that was a great result, it wasn't good enough for us, right? And so we wanted to see how can we make this even faster. And so, this summer, what we had done is we went out and we put out a $100,000 competition in 2 different rounds to see how folks could speed this up. And we had, great support from partners like Amazon and Xilinx and Synopsys that really provided some of the tooling that made this sort of hardware competition possible. And it was really unique competition because this is something that we haven't really seen in the space before, at least in terms of custom hardware with like FPGAs or something to that effect. So the end result of that is we had actually reduced the size of the modulus down to about 1,000 bits to make it a little bit easier for folks, and so they weren't battling the hardware. But we were able to ultimately get a 2x reduction in the speed of that, thanks to Eric, who's here and will be in the hardware session. So if you have any FPGA questions, he is the man to talk to. So since then, we've actually gone and improved the design even further for both power and area savings. So Erdinch, I don't know if you want to maybe come up and just talk a couple minutes about the improvements to the design. And maybe just to preface this, prior to these improvements on the design, the Ozturk method is the fastest known method of squaring that we have seen so far.
So, just quickly, I'm not going to get into the technical details too much because it's, there's a paper online, there's another video from the MIT VDF day. So this was the previous design. I'd like to say that this is to scale. The critical depth is to scale. I use the Python to generate all of these tables. So we have the triangle is the squaring part, and the bottom part, the rectangle, is the reduction part. So what I do here is, so the top part of the triangle is reduced and accumulated on top of the bottom part of the triangle, basically. So the critical path here is the left half of the triangle plus the reduction. And we are utilizing a lookup table based reduction. There's nothing, no Montgomery, no Barrett here. Sorry, we used to do that. But now, with this design, what I figured out is that you can utilize Montgomery to do a bipartite reduction method, which is going to lower the critical path. The complexity is not changing. The number of operations that we are doing is not changing. The reduction part, as you can see, the rectangle is almost the same as previously. But here, with this design, in the critical path, we have the top quarter of the triangle now and the low quarter of the triangle. They're done simultaneously. So we have let's say the adder tree critical depth, and then everything, instead of accumulating everything on the lower part, now we're accumulating things on the middle part. From the top, the reduction is done using lookup tables, just straightforward lookup tables. From the bottom, we have Montgomery lookup tables. So everything is reduced bit by bit using Montgomery reduction. And we can go through the technical details if you want during one of the sessions.
Excellent, thanks for that. Okay, so just very briefly, last thing I want to touch on the VDF evaluation. Why is this important? Well, VDFs are really only as secure as you can reason about the sort of the speed of an attacker, right? And so we want to get as close as possible to the speed of a theoretical attacker who may be able to accelerate this operations. In practical purposes, if you're able to lower this gap between sort of the theoretical lower bound and what you're using in practice, it means that you can either get VDF results quicker with the same level of security, or if you want to have, let's say a VDF output every period, you can run less VDFs in parallel. And so when we started this, we had an Amax of about 5,000. And so this means that you either needed to sort of run the VDF for 5,000 times longer, or you need to run 5,000 in parallel. And what we've been able to do is sort of shrink that gap down to 350 with an FPGA. And as we go to an ASIC, this gap goes, basically another 20x or 15x down to an Amax of about 25. And there'll be some talks today about the lower bounds, and I think it'll be important for us to sort of, as Justin mentioned, improve the clarity of some of these assumptions around that. Okay, so that's enough about latency. So let's now talk about the proof generation process. In the proof generation process, the long and short of it is that the proof gives you the ability to have someone easily verify that you did the evaluation correctly. In the case of the RSA VDFs, this basically means that you do about 10% of the number of modular multiplications as you did modular squares in the operation. The great part about this, though, is that it can all be done in parallel, so this is really a throughput-focused problem. So just to sort of briefly give you some numbers here on what this looks like on various platforms, we've benchmarked an i9 CPU, which is sort of a high-end 8-core Intel processor. the Xilinx VU9P, which is a higher-end FPGA, and then the GPU is a 2080 Ti, which is a higher-end NVIDIA GPU. And what you're able to see is that sort of as we move from platform to platform, we're able to get, order of magnitude size changes. And so for right now, sort of the state of the art is that the FPGA is the platform to go with in terms of VDF evaluation, and the GPU is the platform in terms of generating these VDF proofs. Okay, so let's put that all together. What we've created is something called the VDF as a service. As Justin mentioned, this takes in an Ethereum block hash as a source of pseudo randomness. It will then run the VDF evaluation function on an Amazon F1 FPGA. It will provide some intermediaries to an Amazon GPU that will calculate the proof and then ultimately basically push this out to the API gateway. And this gives you, we're getting about, as mentioned, 26 nanoseconds per square. And this whole proof process, because we're doing it on a GPU, only adds 1% overhead to the VDF. And this is what it looks like. So if you go to vdfalliance.org/service, you can basically get, you can look at the modulus. We're using one from one of the RSA prizes. And then the pi there is your proof. And then last but not least, I just want to talk about, so it's great, now we've got everything, we've got the proof generation, but how do we actually verify this on the chain? So as Justin mentioned, we were looking at doing a single VDF verification on Ethereum, and it was going to take about 1 million gas, or about 10% of the block capacity. And so if you really wanted to have one of these happening every block, that's a significant amount of overhead, is that, 10% of every block, right? So we went and did a whole bunch of benchmarking. We looked at the speeds in the current implementation, so Go Ethereum. We looked at it in a variety of other high-performance libraries like GMP and OpenSSL. And then what we also did is we looked at how accurate was this pricing formula in Ethereum versus the time it actually took to complete the operation. What we found is that it was a fairly accurate pricing formula, but you'll notice that there are a number of these operations down here that are vastly overpriced. So everything below the line doesn't take a lot of time, but still incurs these high verification costs. So thanks to Sean, he dug into exactly how what the underlying algorithms were and how the complexity of the algorithm scales with different modulus sizes and different exponent values. And we were able to devise basically a new pricing formula, which is dramatically simpler and has a higher R-squared value. What you'll notice is that the sort of trend line bisects these data points, and that depends on whether you have an even or odd modulus. So basically, some of the algorithms, depending on the modulus, will use different formulas. So as Justin mentioned, this is sort of our proposal that we'll be moving forward. So that blue line over there is the current gas pricing with sort of not very good efficiency at prediction. And our proposal is to not only sort of improve the pricing algorithm, but also bring this down by about an order of 15. And then just as a point of comparison, often in Ethereum, an elliptic curve key recovery operation is sort of used as the benchmark for what the appropriate gas cost is. And so we're going to take a little bit of a conservative approach and recommend something higher than that. All right, so just in terms of summary, in terms of the Amax and the latency, we have a 10x reduction now with the FPGA platform, and there's 10x more in sight as we go to custom hardware. Throughput, we have about a 30x improvement with the GPU, another 25x in sight, and then the on-chain verification costs, we're looking at bringing these down an additional 15. So there is some help needed. We have this service up and running. If anyone wants to help create smart contracts to actually verify these proofs, if you have other group of unknown order constructions that you want to evaluate with these hardware options that we've built, if you have requirements, if you have uses, if you have use cases, feel free to reach out to myself or really anyone else participating in the Alliance. So looking forward to hearing everyone's talks, and hopefully next year when we come back, we'll be able to show how we brought some of these other use cases into practice. And just a last plug, Simon's going to be giving a talk Thursday at 9:30 at the conference. He'll get into the details about why the performance is different on these different platforms and how to maximize it. So if you're interested in hardware and cryptography performance on different platforms, please give that a listen. All right, thank you.